So, hello everyone, today we will be starting the cell death kinetics. So, we are discussing the heat transfer and sterilization module. In the last lecture we discussed mechanism of heat transfer, particularly conduction, convection and radiation, but in bioprocess this conduction and convections are more prominent. In the conduction, the driving force is temperature gradient dT upon dy, and in the convection driving force is delta T. Further we discussed in the last lecture many times this, particularly when we are dealing with heat exchangers. So, there will be the inlet of hot fluid and cold fluid and outlet of hot fluid and cold fluid. So, the temperature changes along with the length. So, we discuss we have to take care of the Lm delta T log mean temperature difference, that is defined as delta T2 minus delta T1 upon Ln delta T2 upon delta T1. And what is delta T2? If you just see, this is the length. So, and if hot fluid is going like this, temperature is this TH1 to TH2, and cold fluid is going like this TC1 to TC2. Then these two difference will be delta T1 and these two difference will be delta T2. Then further we discuss, as the particularly in the case of convection, as the film is dependent on the fluid hydrodynamics. So, can we have a correlation where we can calculate the heat transfer coefficient if viscosity, velocity and density is known to us. So, we derived, rather we discussed few correlations, particularly Nusselt number is correlated with Reynolds number and Prandtl's number. Now, today we will be discussing the kinetics of cell death. Particularly we are focusing on the thermal sterilization, then specific death constant and activation energy, and then we will briefly discuss how the same can be explained in terms of probability of extension. So, this briefly, this sterilization is important in microbiology, in the food safety, and when we say the kinetics of cell death, this is important because it gives the rate, or particularly you can say it gives the death rate constant, and this is important to see that there should be substantial loss of viability if you want to go with this pure culture. And this death kinetics is very similar to the enzyme deactivation kinetics, and for this, as you have seen, deactivation is a time dependent process. Now, what are the factors which are going to affect? What is the initial number of the cells, and what is the condition for the sterilization? Particularly if you are talking thermal sterilization, then we say what is the temperature, how much time is given for the sterilization, and what is the initial number of viable cells. And the cell death, it follows the first order kinetics. So, if you express mathematically for first order kinetics, then R d rate will be proportional to the n, and the proportionality constant is K d, that is the specific death constant into n. And if you, this n is the number that can also be expressed in the terms of cell concentration. If the n can be replaced with the x, if you want to write in terms of concentration. Now, R d is minus d n, because number is decreasing, d n upon d t equals Kd into n. So, if you integrate it, so this will be minus dn upon n equals Kd into dt. If you integrate, it will be ln n upon n naught equals minus Kd into t. So, we write n naught as n naught into e to the power minus Kd into t. So, in this way, this death rate constant and time and n naught, these three factors decides what is the final number of viable cell after sterilization. And experimentally, if n and n naught are given to us, we should be able to calculate the other parameters. For example, if you just see, if I plot ln n upon n naught equals minus Kd into t. So, if I plot n upon n naught in the log axis and time, then slope will be, this is the slope, you can get the value of Kd. And further, what we are seeing over here is at different temperature we are getting different slope. The slope now is dependent on the temperature. So, what it says that Kd depends on temperature, and how it depends on temperature? Through Arrhenius equation that we are going to discuss. So, here is one quick example. So, it says a bacterial growth media is subjected to sterilization. Its initial number of cell was found to be n naught is 1.5 into 10 to the power 6. Sterilization was done at 121 degree centigrade, 15 psi, and number of cell after sterilization was 2.3 10 to the power 5. You need to calculate the time, and this decomposition rate constant Kd is given as 0.35 hour inverse. So, T will be simply ln n upon n naught divided by Kd, and you will get a straightforward answer as 5.37 hour. This is very simple calculation. Now, you just see, this is the death rate of two different bacterial species. This is the Bacillus stereothermophilus and this is for E. coli. So, you can say this is following a straight line, but in both the cases what you will see, if there is a higher temperature, there is a faster death rate. So, what it says, Kd is proportional to T, and how it is related with the T? Through the Arrhenius equation. So, Arrhenius equation says Kd is proportional to e to the power minus E naught d upon RT, and E naught d is activation energy for the death, and the proportionality constant we write as A e to the power minus E naught d upon RT. And the typical value of E naught for microbial death is in the range of 250 to 290 kilojoule per mole, and nutrients typically have a lower activation energy value for thermal deconstruction than the microbes. So, considering this activation energy for the nutrients and cell death, it is desirable that high temperature and short time sterilization should be designed in such a way to kill the cells faster while preserving the nutrients in a better way. Now, I have listed one example here. So, it says consider the following data and determine the activation energy for thermal death of Bacillus subtilis spores, and also determine the time required to kill 99% of spores at 100 degree centigrade, and these are data at different temperature. The Kd value is given. Then first what is needed here is at 100 degree centigrade what will be the Kd value. So, how we will find the Kd? Kd value is Kd is A e to the power minus E naught d upon RT. So, what is not available to us is A and E naught d, activation energy. So, we discussed in the last slide that if you plot ln Kd versus 1 upon T. So, what is happening here? It is ln Kd equals ln A minus E naught d upon RT. So, if you plot ln Kd and 1 upon T, then the slope will be E naught upon R and the intercept will be ln A. So, from there we got the value of E naught d as 225 kilojoule per mole and value of A as 6.52 into 10 to the power 30 as a constant value. So, in the last lecture this is the typical value 250 to 290, we are getting in the similar range 225 kilojoule per mole. Now, at 100 degree centigrade we can calculate the Kd. A is known, activation energy is known, R is gas constant 8.314 joule per mole degree Kelvin, and T is 100 degree centigrade means 100 plus 273.15 373.15 in Kelvin. So, we got Kd as 0.23 minute inverse, and once Kd is known, now we can go to the second part of the question that says estimate the time required to kill 99% spores. What does it mean? It says there is a relation between N as 99% are killed. How many are left now? 1%, 0.01 of N naught. So, if N and N naught is known, we can quickly find the T as ln N naught upon N divided by Kd. So, this is known to us, and Kd we have already calculated. So, we will get 20 minutes. So, in this way it suggests that this thermal death rate depends on the temperature. Now, further we can discuss or express this sterilization in terms of probability of extinction. So, let us say the probability of extinction of total population is capital P naught T. So, capital P naught T is defined as 1 minus small p t to the power n naught. N naught is number of individual cell present and small p t is probability of cell being viable at T. So, T is the viable cell, so 1 minus p t will be how many cells they are dead. So, this is viable and 1 minus p t means how many are sterilized, and N naught is the initial number of cells. So, based on this expression, now we can next write the expected value of number of individual cell. So, how many number of individual cell will be there, because how many cells are surviving? Small p t. Then how many total number of cells were there? N naught into small p t. So, this is the expected value of number of individual cell present at time t, and this is the variance. What will be the variance here? Variance will be N naught p t, expected number of cells, into 1 minus p into t. So, this is the variance about this number. Now, again we can write the expression of specific death rate. How do we write specific death rate? Kd If you remember, how did we write Kd in terms of total number of cells? That was 1 upon n dn upon dt. And what is the expected number of cell here is the n naught pt. So, how this will be in terms of now Kd as minus E expected number of cell at time t to d upon dt expected number of cells at nt, and nt is n naught into pt. So, n naught is a constant, but it will be cancelled out. So, we will end up with minus d upon dt ln pt. Now, this says pt as e to the power minus kd into t. If you integrate it, small pt is e to the power minus k dt. Now, if you recall the earlier expression, I will quickly. So, it says n naught, n equals n naught e to the power minus k dt. So, it says n equals n naught e to the power minus k d into t. Now, what will be the expected number of cell at the time t will be n naught into pt. So, n naught, what was pt is e to the power minus k d into t. Now, if we compare this expression and this expression, so what it says is this pt t is directly equal to e to the power minus k dt. So, this thermal date constant is related with probability of cell being viable at time t. Now, we will have one example, then it will be clear. It says assume the probability of failure within the acceptable range is 10 to the power minus 3. Now, just see what it says is this is the probability of extension. Now, it is saying probability of failure. So, probability of failure will be 1 minus probability of extension. N naught was 10 to the power 8 and sterilization temperature was 121 degree centigrade. You need to find the value of T, and Kd is given as 1 minute inverse. So, we can quickly write this 1 minus T is will be 1 minus P t to the power n naught, and this P t can be replaced by e to the power minus k d t 1 minus e to the power minus k d t to the power n naught. Now, all the parameters are known, but you have to find the value of t here, and the t will be coming out to be 26 minutes. So, in this way the sterilization can be expressed in terms of probability, either in terms of small p t, in the terms of capital P t, or in the terms of n t, number of cells after time t. And one more term we can quickly discuss here. It says decimal reduction time. It means the time taken for the number of viable cell to decrease by 10 folds. 10 folds means n naught upon n equals 10 or n upon n naught equals 0.1. So, if this is known, we already know T will be, rather we write T d will be ln n naught upon n divided by k d. Then this becomes 2.303 upon k d, that is it. So, if decimal reduction time is given, so we can quickly understood its significance, and it enables us to calculate the value of Kd. So, here you just see one example. In situ sterilization was performed for autoclaving the medium used for the production of biocyanine by Pseudomonas aeruginosa. During the moist heat sterilization at a specified temperature, it was observed that after 12 minutes, T as a 12 minutes, the probability that any contaminating organism is 0.02. It means this is small pt, and calculate the time required to reduce the microbial population by 90%. It means you said you have to calculate the decimal reduction time. So, what is given? Small pt is given, small pt is 0.02 equals e to the power minus k d into t, and t was 12 minutes. So, we can straightforward find the value of k d, which is coming out to be 0.326 minute inverse. Now, we have to find the t d, time decimal reduction time, and the formula is known. T d is, you can write T d as 2.303 upon k d. This is coming out to be 7.06 minute. So, in this way, this we should be able to understand the sterilization in terms of decimal reduction time, in terms of number, or in terms of probability. So, I will stop here. So, today we discuss the kinetics of cell death in the terms of number of cells. The same can be written in terms of concentration of the cells, and if number and concentration are not given, then it can be in terms of probability of live cells or probability of extension. And further, what we have seen, the k d depends on the temperature and it follow the Arrhenius equation. Thank you so much.